Dom, show us which direction we should be going in.
Oh, God.
Well, this is the British Railways lecture, you know, the arrow that don't know which way it's going. Right, well, good evening, everybody. Thank you for all coming. I'm going to talk about direction finding, which before I got involved in satellites and all that kind of clever stuff, I was involved with direction finding from out at sea because of the nature of the job. So it's in my blood. It's a fascinating subject. There's lots and lots of learned papers out there that you can read. It's there's books been written on it, and it goes back to the dawn of radio. So it's but I'm going to keep it fairly simple this evening. I'm going to concentrate on one antenna, and there are many different types of antennas that can be used for direction finding, depending on what frequency you're using. I'm going to concentrate on one particular type of antenna and how it was used in both a commercial and a military environment. The loop antenna. Now, when Heinrich Hertz was doing his research into radio in the latter part of the 19th century, he got a bit of wire and bent it in a loop and discovered that it actually turned it into a directional antenna. And if we place the loop in the path of the oncoming wave, side on or end on, you get a nice lot of signal. So this is where you've taken your loop, the signal's coming in that direction, and the signal is hitting one side of the loop first. What happens is that as the signal hits the antenna here, it starts to do what all antennas do. It gets currents induced in there and induced in that side. And there is a difference there. You get RF AC out of there, because what's going on this side of the antenna is different to what's going on that side of the antenna, and you get maximum signal. And you just connect it to your receiver, and then it's all easy after that. If you take the same antenna and you turn it broadside on to the incoming wave, so you're actually holding it like that and the wave is coming towards you, you're getting the same currents induced in that side as you are in that side, and when they get to the middle they null each other out, so you don't get anything. So suddenly we've got an antenna that we can turn it that way and get maximum signal, turn it that way and we get zilch. That's the theory anyway. There are lots of math, obviously, with all antennas. There's plenty of maths you can read about this online, but that is the basic fundamental idea of a loop antenna. And from that we can build ourselves a polar diagram where there's the loop there, we've got maximum response on that side, and that side, zilch there. That's a fundamental principle. That was discovered right back at the very early days of radio. And there are also, Jeff's kindly lent me these props. There's a bigger one here, which is this is a receiving loop. Same thing, stick that on a rotator, and away you go. You've got a directional antenna with a little antenna. That's an active antenna. There are numerous designs out there for receiving and transmitting antennas. We've got one problem, that we can only see in one direction. What if we want to look at 360 degrees? So, Bellini-Tosi. who were they then? This was one of the first direction finding systems, and it uses two loops set at 90 degrees to each other. Basically, you've got two loops. You put one going that way and one going that way, the same size. You can have the same size loops, as we shall see. And you think, well, that's it. I've got all 360 degrees covered then. So, Mr. Bellini and Mr. Tosi, who were naval officers in the Italian Navy in about 1907, came up with this idea where if we take two loop antennas, one north-south, one east-west, if you put that on a ship, that's forward and aft, port and starboard, and you attach each loop to a coil. Now, obviously, there's some electronics involved in that, but basically, you attach each loop to a static coil. And those coils are going to produce a magnetic field that's proportional in strength to the signal coming in there. So if you have got a signal coming in from 45 degrees, you're going to get equal strength in both coils. Or if you've got one coming in from the north, you're going to get strong signals there, weak signals there, or no signals there. So how do you get it from there into your receiver? You add another coil. And this coil is moved by the operator. And basically, you can rotate it and sample the signal from each coil. And that's the rotary coil. So that can be hand-driven, it can be motor-driven, but it's a transformer. What you've got is a transformer, and you're going round and round sampling the signal from each loop. But you will still have 2 points of maximum signal. You'll have one over there and one over there, or one over there and one over there, because both loops work in that way. You get two maxima and two minima on each loop. This device was known as the Bellini-Tosi goniometer. If you've never heard the word before, a goniometer or goniometer is with all DF systems, even the great big land-based ones that take up a whole field, right in the middle, you've got a spinning goniometer. So Ettore Bellini and Alessandro Tosi, they designed that, and they took out a patent in 1907 for that. And then they decided that they couldn't really develop it on their own, so they sold the patent to Marconi, who was a better businessman, and they started working for him. So Marconi's picked it up and run with it. But it became known as the BT antenna. Nothing to do with British Telecom. It's Bellini-Tosi. And it's had quite a long life. So, next thing, I've got a signal. It's coming from there, and it's also coming from there. Which direction is it coming from? For example, if I was standing here with one of these antennas, and I was pointing it towards Droitwich, I'd have a very strong signal there, and I'd also have a strong signal over there. So how do I know if my signal, other than identifying by listening to it, is coming from France or coming from the Midlands? So it's, and this omnidirectional. And that usually, by design, in most designs, sits in right in the middle between the two loops. There are others. So the signal from the sense antenna is combined with the signal from your rotor, from your goniometer. And then the resulting signal is phase compared with the sense antenna. And what you find is that the true direction will be the one within phase, because the sense antenna will be in phase with the true direction, but it will be out of phase with the other max. So you've got electronics built into that, and you can do all this mathematically, but that gives you an idea, and all you need to be able to do is to have some sort of switching arrangement where you can switch the loops out and switch the sense antenna in, so you can determine which way the signal is coming. So there is an early design, and if you look carefully, there's the two loops, north-south, east-west, or forward and aft, port and starboard, and you notice how it's mounted, because it has to be up high. It has to be away, particularly on a ship, it has to be away from the superstructure. Typical, if you get any superstructure involved, you're going to have a problem. And one of the things that, when I was involved with it, if you went into a refit and the dockyard mateys had been doing some work on the masts and they'd added on a few bits or changed the shape, the first thing you did when you come out of that first day at sea trials, you're doing a DF calibration. And I'm sure Peter will remember DF cals. Yeah, there's another one there in a museum. These are early designs. And there's one stuck on a ship. Bellini-Tosi antennas. So what you ended up with is, where is it? Well, here's a little tugboat, and then you can see top of the shot there. Here is the Queen Mary, the original one, number 534, 1935-ish, from John Brown's, with the new one there. But if you zoom in on the bridge of this one, you will see a little DF loop there. Another one there, little cargo ship right on top of the mast. The QE2, which is now out in Dubai. This is the QE2 as just after she was built, and there's a little DF loop on there. If you look at later photographs of the QE2, she hasn't got it. It's been taken off. Because the technology went on, wasn't being used. When she started having satellite dishes stuck on her, no need for it. Is it a modern system? Well, here's an old tramp steamer from the 1930s, and just behind the bridge there is this is taken in the 1950s, I think, but that is one of the original loops. So we've got a system. We've got our system of direction finding. What we need now is to some kit to connect up to that antenna to allow us to use it to find out where we are. Well, the first commercial use at sea of this antenna, pretty obvious, search and rescue. Back in the days when merchant ships communicated with each other with Morse code, CW, the international calling and distress frequency was 500 kilohertz. So you called, if you had traffic to pass, you passed it to shore stations. There were 2 periods in the hour where all transmission ceased, 0 to 3 minutes past, 30 to 33. If you look at any pictures of an old radio room clock, you'll see there's a green area and a red area. So you listened out. That was when anybody that was in trouble could get on there with SOS. And hopefully somebody would be able to DF that. Marine and air navigation. Now I know this is marine, but they used a system like this in early aircraft. So in the early 1930s, 2 chains of radio beacons were established, one for the marine, one for air. Now originally, marine beacons had 2-letter Morse IDs. Air beacons had 3. So if anybody finds a 2-letter beacon ID today, then you're going to get a prize, because they've virtually all gone. All that's left are 3-letter ones, the air ones. What you need to know to use it for navigation is you need to know exactly where those beacons are. So all the information that we need used to be published in all the annual nautical and air almanacs. Things like Reed's Nautical Almanac, the Macmillan Nautical Almanac. All of that contained lists and lists. And most famously, Admiralty List of Radio Stations, Volume 2. And I can see Peter smiling there. Admiralty List. The Admiralty List, now, you know about the Hydrographic Office up at Taunton. They publish this. There are 5, 6 volumes now. Volume number 1 used to be general, all the coast stations. Volume 2 was all to do with navigational aids. And Volume 2 is still published. But you won't find any beacon signals in there. It will tell you all about GPS and all the rest of all the other navigation, modern navigation aids, but it used to have lists of beacons in. So that was what I used at sea, and I'm sure Peter probably used it at sea, and it was forever pasting corrections into it as things changed. Today, where can you get your information? Well, some of these beacon signals are still around, and there are various enthusiast websites that you can get lists of these and their frequencies. A chap called Alan Gale, G4TNP, keeps a fairly up-to-date website. There's a guy in the States, Bill Hepburn, he does it. But for those of you who've ever read Radio User magazine from a few years ago, there was a guy called Robert Connolly who used to write in there from Northern Ireland, and he has still got his website running. Non-directional beacons.
The one at Exeter and the one at Nuclear are still operating.
Yeah, they are. They are.
338 and 347 kilohertz.
Yeah. So, beacon signals. What did these beacon signals consist of? Well, they were originally on off-key carrier, A1A. We call it CW, but that's not really CW because it's not continuous. Or amplitude modulation using an on-off-key tone, which is A2A, or modulated continuous wave. So originally there were 2 frequency ranges, one for air and one for marine. And the modulation frequency would either be 400 hertz or 1200 hertz. 1020 hertz. And I've got a recording here, which I'm sure some of you have probably heard before. This is YVL, this is an air beacon, YVL, Yeovil. This is the Westlands factory at Yeovil, Leonardo's, as it now is. And they're using, you can see there, they're using a carrier, and they've got a key tone in either sideband. And you can play around with your receiver. That's a 400 hertz tone. And all I've done is go to upper sideband. But that's the beacon there. And that's on 343 kilohertz. And that's easily heard down here. That's all it is. It goes like that 24 hours a day. Right, what do you need? Right, well, this is the sort of thing you might have had on your ship in the 1930s. So you would have tuning arrangements and a coil built into there. This was quite a small one. Some of the early ones are quite chunky, but this is a 1930s one. By the beginning of World War II, you might have had something like this. This is a commercial one, but it was also supplied to HM ships. You've got a tuning dial over here with a tuning control. You've got a band switcher there. This is your goniometer in here. This is where you swing your coil, and this is where you read your signal strength. And you have got switches on here to switch in and out the sense aerial, so you know which direction it's coming from. Quite a hefty piece of kit. You know, two-man lift, this sort of thing. It's not exactly something you're going to give yourself a hernia about. That's a big lump. And of course, setting this thing up, when you have to have all the amplification and the phase for each channel to be absolutely set up correctly. Exactly the same length of antenna cable to each of the, you can't have one bit of cable, one loop with a bit longer wire, it will muck it up. Yeah, sure.
On the pictures you showed of the cross things,
Yeah.
one was larger than the other one. But I know loop aerials are very delicate.
Yeah.
The length of them is very important.
Yeah.
So one was significantly larger than
Yeah.
the other one.
Well, that was by design.
Oh, right.
Because what you've got to do, this is going to be up high on the mast. It's got to be strong.
Yes.
It's got to withstand the weather, and that's the issue. If in the 1930s you were a multi-millionaire, you might have owned a yacht. So there you are. You can have your very own radio compass. Now that's not exactly portable, is it? That's an advert from an American radio magazine.
Thick or stormy weather.
Yeah. So, but so that was what you might have been using in the 1930s. Here, you've only got one loop. So what you have to do is you have to swing the loop. You're only using one loop, and that's reduced. Whereas with a fixed array, you can't go up the mast and swing the loop. By the 1960s, if you were a radio officer on the ship, you'd be using something like this. This is a photograph taken off a radio room of a ship in the 1960s, and what he's using is a Marconi Lodestar, which is the same idea as the one we saw before. We've got a tuning dial this time on the left, and we've got the compass on this side. Some of them had a compass ring in there that was slaved to the ship's gyro. So as you change course, this little thing would click round inside there, and all your controls are under this panel here. Again, in the 1960s, if you had a yacht, you might have had something like this. Now, Jeff has kindly brought this in, and this is a portable DF set from similar time. You've got an antenna there, but more importantly, you've got a rotating antenna here. That's a ferrite bar. Now, interesting things happen to the loop antenna. When you take the loop and you wrap it round a ferrite bar, it changes the polar diagram by 90 degrees. So any mathematicians amongst you can explain that, but it does change the direction. Because
so the null is 90 degrees out.
yeah. So, but you can build that in to your compass card there to correct for it. So that is why when your domestic receivers, when you used to have a play with your little domestic transistor radios and you turned them, you thought, well, I've got a strong signal. Yeah, because they've got a ferrite loop in there, which is basically a loop that's wrapped round a bar. And it just makes instead of having the maximum on there, the maximum is now on the side. But then you've effectively got lots of little loop antennas there. So that's the sort of thing you might have had in your yacht, where you can take a bearing of one of the beacons. Most of them also, some of them had the medium wave band included because you could take a bearing of the light program on medium wave or the home service, provided you knew exactly where the transmitter was.
Radio London, the good old power ship, used to give its exact position every hour.
It did. Well, there you are.
There you go. So you could home in on it.
So you could home in on it.
Loud.
Yeah, brilliant. And then eventually, as electronics improved, we got something like this, where you've got a tuning dial on the front and the compass. So again, Jeff has kindly brought one of these in. And I know this works because Jeff lent it to me once and I took it home and had a play with it. And that's tuned to 196 on there, just off Radio 4. So you point it there and you've got a meter reading there. So you go for max, and then what you can look at in there, you've got a compass card in there, and you read the bearing off there.
Compass.
Yeah. So you just do that. Ideal for the weekend yachtsman. You can take a beacon. So having got all this information, what are you going to do with it? Right. Here is the English Channel. And here you come chuntering up dirty British coaster with a salt cake smokestack. And you just made yourself a cup of coffee and the skipper phones down and says, I can't see where I am, what I'm doing. I can't see any lighthouses. Where am I, Sparks? So you grab your headphones, away you go, and you start tuning some signals. So you find one there, which is on the Lizard. You find another one there, which is at start point. And then you find another one there on the Isle of Wight. And just for good measure, you find another one there on the Channel Islands. So you've got these 4 bearings. You hot-foot it to the bridge, and they plot these on the chart, and you're the skipper's mate. You get a bonus next month. So these are low frequency, these are MF beacons. And they travel very well over sea. You're using ground wave. I can remember going on passage across the Indian Ocean where there's nothing before the days of satellite, and the navigator coming down the wireless room and saying, I need some help. Because we were navigating by dead reckoning. Those of you who've never done navigation, dead reckoning is basically, I'm going on this course at this speed, so in 6 hours' time, I'm going to be over there. Or am I? Because the wind is blowing there, the tide is going there, who knows where I'm going to be? But I've got so many...
Well, obviously, donkeys years ago, they used a sextant and the clock.
Yeah, that's right.
They fall back to that.
Yeah, you've still got that, but we've now got this wonderful network of radio beacons. So the navigator comes down and says, I need some bearings. So you pick out your annual list of Admiralty list of radio signals, and then start swinging the dials and try and get him some bearings. And it does work, and this works over hundreds of miles because it's low frequency and ground wave. Peter?
They can only use the sextant if they can see.
Yeah,
There's no cloud cover.
No cloud cover.
You have to have a horizon.
Sometimes they're right in the middle of nowhere.
You've just
You've
got
clouds, you can't see any stars,
Yeah.
sun, or anything. So, yeah, dead reckoning.
So that's how you navigated, and that system continued up until about the 1970s, and it was along with other systems that were coming along. You have LORAN, which is long-range navigation. There's still a LORAN signal on 100 kilohertz. You had the Decca Navigator, which were, these were based on systems invented during the war to navigate bombers. And then eventually, of course, we got GPS. But this was where it started. It was all to help. And of course, you could do this out of sight of land, because radio signals. So that was the commercial maritime DF. So I'm now going to have a quick look at some of the military uses. Well, obviously, the first most obvious one is, where is he? Where's the bad guy? Determining the enemy position. Obviously, search and rescue. And then some marine and air navigation. Interesting to note, I've got a friend who works with me at the museum who is a British Airways pilot. He's about to retire, but he's still working out of Heathrow. And he says commercial airline pilots today still have to learn Morse code. Okay, albeit only to a few words a minute, but they have to fall back on the MF beacons that are still in existence, and of course the VHF beacons. If you've got a VHF radio, tune it to 112.5 megahertz and you'll hear Berry Head beeping away.
Didn't that happen very recently when von der Leyen's plane coming into, was it Budapest? The GPS signal to it got blocked.
Yep.
And
So
they
you
had
have to go
revert
back, you have to fall back.
Yeah, they fell back on the NDBs.
If you ever, on a busy day, if you ever look over southwards across Berry Head and you watch the vapour trails, you know, it is, how do I get to Manchester? Oh, go north, turn left at Berry Head. You know, and they're all doing that in the sky. Right, first thing we're going to do then is make some improvements to our system. The military have got slightly more demanding characteristics. So we've got the same thing. We've got a cross-loop omnidirectional antenna, but in the early 1920s we see the invention of the cathode ray tube. Now, for those of you who remember your theory, the cathode ray tube, you've got two sets of plates in it, the Y plates, which are your vertical axis, the X plates here. These are the X plates, that's the Y plates, and you've got a brightness grid at the back. And this system was designed by a famous name, Mr. Watson Watt and Mr. Hurd. They were working for the Radio Research Laboratory, and in 1926 they were asked to come up with a system for finding thunderstorms. And this is what they came up with. They took Bellini-Tosi's system and stuck it in the back of what would have then been a very small CRT. So static coils are replaced by the deflection plates. North and south, we'll connect those to the Y plates. East-west to the X plates. So if you've got a signal coming in your loop there, what you're going to get on the screen is you're going to get an ellipse as the dot swings between the two plates of the oscilloscope. One of the things that when I was looking at this, I thought, I wonder how many young technicians these days, because everything's flat screen, it's all done with in hardware, but you've got X plates and Y plates, but it's still called it X and Y, you know. The sense antenna is connected to the brilliance. Now this used to be because this used to be a big valve, this was the brilliance grid. That's where you put your sense antenna. And there were some antenna improvements made. And we end up...
Don, theoretically, with a standard analog oscilloscope, a couple of loops, could we actually do that here in the club?
Yes.
Yeah.
You could do
That
it.
could
Yeah.
be a very interesting one.
There
to
is
do.
a video on YouTube of an American that did it. Yeah.
That could be really interesting to do
Yeah.
one night for a bit of fun.
Got a club oscilloscope.
Yeah, yeah.
Yeah. So this was what was invented. This was what I can remember as being called the Bellini-Tosi S25B frame coil. Basically, you've got your two loops in there, and this is all made from, it was originally made from plastic, was later models were made from fiberglass, sense antenna going through the middle, and later you had a test loop put in there at 45 degrees, allowing you to inject a test signal from the radio room to calibrate the set. So you had a built-in calibration facility. This is an early model. There's a model of it stuck on a roof. And if you can stick it on a roof, you can stick it on a ship. So it's stuck on a pole. And this went on, this system went on to keep make a significant difference to the Battle of the Atlantic, as we shall see. So this was the sort of thing that was deployed in the late 1930s. You've got a much better receiver. You've got a very small oscilloscope here, and you've got your sense coils here. So you can swing there, and you've got your various switches there. This was known as the FH3 in the Navy. It was known in the US as outfit DAR by the US Navy. And the receiver's called a B21, all made by Marconi. That's what the receiver's like. And that's where you controlled it from. So that's what the Navy went into the war with in 1939, and it was just the coming thing. So that's what they started the war with, and then in 1943-44, it was replaced by that. Much more compact, although it still takes you two of you to lift it. You've got a lovely big CRT in the middle, tuning dial there, tuning controls there, and of course all the other bits and pieces that go with it, power supplies. Now it was known as FH4 or AH6 because it was also used on air stations, and it was also used on aircraft carriers, but not to go and find submarines. So that's where the Navy were with high frequency direction finding during the war, by the end of the war. There you are. This is a typical shipboard installation during the war. you would have sat there in the cabin for hours on end. There's the receiving outfit. Around the edge here, driven from this motor here, you would have a compass ring driven by the ship's gyro. So this used to click round and round and round when you were tuning around. There's your antenna connection box there, 4 leads going up, power supply up here. There's another CR100 receiver over there on the top. Yeah, that's another installation. Are there any left? Well, apart from that one, which is in Halifax, Nova Scotia. Yes, there are. I know where there is one. This is one that was rescued. It is currently in the reserve hangar at Air Station Yeovilton. It was originally owned by a chap called Arthur Bauer, who's written, a Dutchman, who has written many good papers on HFDF. One day I'm going to twist somebody's arm to get it out of storage, but it's a beast. It's like, those are the front panel controls. Look at all these controls down here, and there's another load of controls on the other side. There are actually 124 adjustable controls on this thing, because if you take that side panel off, there's all sorts of little screwdriver adjustments you can make. It took a day to calibrate it. You sat at anchor and the tug going round and round in circles round you, somebody on the bridge calling out the bearings, and you tweaking, tweaking, tweaking. Because when you had your ellipse on the screen, any gain error between the fore and aft loop would cause a bearing error. Any phase error would cause the ellipse to go fatter or narrower. So you had to get it all absolutely lined up. But once you've got one that's lined up and you deploy this, you can get a bearing accuracy around about 3 megs of plus or minus 1 degree. It can be absolutely spot on. This is a picture of the front panel and all sorts of controls for doing things. But when you were actually using it live, that area of the panel is what you were going to, particularly this switch here. This is your sense switch. This is what you swung left and right to find out. What you needed to do is to find out which way it was going. Right, how was it used? Well, the Battle of the Atlantic. I don't know if you know, currently there is a series on BBC Two talking about the Nazis and U-boats. It was on last night, I think. And they haven't mentioned this yet. But this particular piece of kit was one key element. The Battle of the Atlantic was a battle that we had to win. So there's the Atlantic. Now, when you see a convoy of 80, 90 ships moored, say in the bay, if we had it moored out here in Tor Bay, you'd say, my goodness me, ships from here to there, everywhere. When you take that convoy of 80 ships and you put it in the middle of the Atlantic, it'll be a dot. And that's what the U-boats had to find. So out they go, doing it, sent them out there. There they all are, swanning around, looking for convoys. They were being talked to by German Naval High Command, and they used HF and they used VLF. HF, when they had a chance to come to the surface and use their HF antenna, VLF, they could trail a wire on the top. we needed to know where these guys were. So we've got two lots of communication going on, VLF and HF. Where's that coming from? That's coming from transmitting sites in Germany and in France. And these were quite powerful transmitters. And of course, we were intercepting those transmissions. Various sites around the country. All the stuff ended up at Bletchley Park, which I know you know this. I pinched this off another presentation. So, and it all went down to the Operational Intelligence Centre in London, where they compiled it with other sources of information. And what they wanted was to send a message out to the convoys where the U-boats were. Now, it was really only a general message. We could DF the U-boats from the UK when they were using HF, but it was, you know, the cocked hat of DF was quite wide by the time it got out there. There were two commanders in a convoy. There was a convoy commodore who looked after the merchant ships, and there was the escort commander. So they worked together. The escorts their job was to protect the escorts. And often there was a conflict between chasing after a U-boat and protecting the escort. Their job was to get that stuff over here. So that was the decision was made what to do. So how can I use that setup to find out where the submarines were? Right. Here's the front panel of my FH4. U-boat radio operators were told to keep their transmissions very short because the Germans knew we had this. And you'd see the traffic light. That's the sort of thing you'd be presented with in about that time frame. So he would be calling. So what you want to do is you want to know, is he over there or is he over there? So grabbing your sweaty sense switch in your hand, you swing that one way and you get a tadpole there. And then you swing it the other way, and you get there. So we know that that is the true bearing of the transmission. And that's quite slow. It could be a lot quicker than that. You'd have to, you know, you'd only swing it once and do it. And this is where you're switching out the one loop and switching in the sense antenna and determining which thing, and where it's in phase, you know that's a true bearing. Now, I thought there's got to be somewhere out there in this internet wide world, somewhere's got to have a video of it, of this being used. Do you think I could find one? Well, I came up, I found, some of you remember a series in the 1970s called Tomorrow's World? A presenter called William Woolard. Yeah. Well, he made a series of films about Bletchley Park and all the stuff like that. And he made one on the Battle of the Atlantic. I tracked down a copy of it, and there's about a 15-second clip of film of somebody using an FH4.
It's a brilliant imitation.
fitted to Allied escorts. It was nicknamed HAFTA, which stood for High Frequency Direction Finding. If it could pick up a radio signal from a transmitting submarine, it could plot the boat's position very accurately. But the Germans knew this. As a result, they kept the U-boat transmission to a minimum to follow the escort ships.
That's it. That's the only clip of film I've ever seen of one of these. And I came on it by chance. But you got an idea of what was doing. So once you got the bearing, there's the convoy, there's the escorts, there's the bad guy there. What they would do, the first one to spot the convoy would come up, send a sighting report back to Germany, and also communicate with his mates on or about the 80-metre band, at 3 megs. So we had ground wave. So if you had ships fitted with HFDF, you ping that, and then it's over to the convoy escort commander then. You know where the submarines are. What are you going to do about it? Are you going to turn the convoy? Are you going to detach an escort? What are you going to do? So that would be what you do. You find out where they are. You had 2 options. You can either detach your escort, but you could also have air cover with you. One of the things they did during the war is they took merchant ships, as long as they had a pumpable cargo, like oil, fuel, everything, they just cut the superstructure off and stuck a deck on it. And they could put half a dozen swordfish on there, and you've got what's called a Mac ship. Wooden planks, and you could launch. And what you're trying to do is stop the submarine diving. The submarine would have to come up to charge its batteries once every 24 hours. If you could find it while it was talking to somebody, if you could damage it enough just to stop it diving, then you could go in and shoot it. And all the time, the Battle of the Atlantic is a technology war, really. So you drop a depth charge on it, do some damage. And this is about the technology side. They knew we had radar, so the Germans came up with a very, very rudimentary warning receiver who could ping our radars. That's how they found us. But out of that came warfare, electronic warfare. Right, a bit on the search and rescue now. So if you were a young pilot and you've just taken off from the carrier and you've been told, right, we think there's a U-boat over there, off you go and find it and drop a depth charge on it. You triangulate it, you've got a rough range and bearing. So off you go and see what you can do. So you do that, you carry out an attack, and then you've got to find the carrier. You want to go home. Right, so that would be typical of the radio transmitter and receiver that you would have in the back. And the guy sitting in the back seat, who was the gunner, was also a telegraphist. He was a TAG, telegraphist air gunner. And you notice that's his antenna. Now, I had the privilege to meet one of these guys last year who flew in Barracudas. And this is the story he told about how you tune your antenna. Was he used to hold the key down. He just used to trail out and it'd be spinning around like that, and he'd be watching the SWR meter, and as soon as the SWR meter went bonk like that, he just put his boot on it and started transmitting. I said, you're having me on it? He said, no, it's true. he was 90 something years old, but it was basically you trail out enough wire until you get a match with the transmitter and then you hit the key. Needs must. So you've got to get home. You've got a transmitter. So what you'd have is you'd have one of these. This is a bathtub Morse key. This was standard fit to most aircraft during the war. It's called a bathtub because it looks like a bathtub. But for those of you who've never seen one before, you open it up and the whole thing's upside down inside. The idea of putting it in that is to stop the sparks. The fact that your connections here are just screw terminals, don't worry about that. And then you've got a little clip to go on the back. One of the things you can do with that clip is you can slide it forward and you can slide it over the handle and it holds the key down. That's quite useful because if you've got an engine failure and you are about to ditch in the sea, you want somebody to come and find you. So you tune your radio up, they're listening for you on the carrier with a DF set. So you just bang that off and then you start getting the life raft out and thinking about looking after yourself. But if your aircraft's all right, you would hold it down for 15, 20 seconds, allowing the aircraft carrier to take a bearing of you. Take it off, and then they would send you a little message, fly down the reciprocal of that bearing, and we will be waiting for you. That's the theory. Yeah. So there is a model of a Mac ship, and I don't know if you can notice that at the front of it here is a mast with a Bellini Tosi loop on it. And I've got a blow up of it there. So the model maker was correct when he made that. And I've got a photograph of one here, anchored off Greenock in 1943, and there's the DF loop there. So this is, they weren't used too much in finding the U-boats because they weren't going to go off and do it, but that was there mainly to serve as a search and rescue job for the ship, the aircraft. So what happened post World War II? Well, that FH4 carried on until the mid-1970s. So when radio operator second class Andrews went in there, I was trained on FH4. Nothing was told to us about how the Battle of the Atlantic or anything like that, but we were trained on it. And then I ended up later on teaching it. But it was replaced mid-70s to late 80s by this guy, FH5. And that's the great big thing there. This is the main receiver unit. This is the oscilloscope unit here. If you look at that receiver a bit closely, does it remind you of anything? Rakel 17, well done. It is in fact two Rakel 17s inside one box. And they called it the Rakel 153. The sensing was a little push button here. You just pressed it and you got two pips. But amazingly, the antenna was exactly the same. It used the same antenna. So this is a picture of HMS Glasgow, about 1981. And lo and behold, there's an S-25B on the top of it. 40 odd years after World War II, and we're still using the same antenna. Get value for money out of your taxpayers' pound. Well, that's right. So, marine MF beacons are now obsolete. because everybody's using GPS. But there are still some air beacons around. Now, I've put this in. The RN does not need any HFDA capability, and there was a thought about we don't need it anymore, so they got rid of the FH5. That's gone. That left service in the late 80s, early 90s. Because if you're using satellite communications for your day-to-day communications, so are the other guys. So the Russians are using satellite communications. I say the Russians, you know, that might be the next lot. But I did read today there is some ships being fitted with a system called Shaman, which is a sort of signals intelligence suite. It's going to have an HF antenna, DF antenna, but you ain't going to be able to see it because the antenna is the guardrail around the thing. And you think, well, hang on, that's not a circle. Ships are shaped like that. But by the use of delay lines, they actually reconstitute that into a circle. But I don't think they're going to find many Russians on HF. So you'll be able to read that nice and slow. Right, gents, thanks very much for listening. I hope you enjoyed that. It's a quick look at one facet of marine DF. There's, you know, it's a big subject, direction finding, and you get into all sorts of antennas like Webers and Adcox, and it's bad, but lots of good stuff. Thanks for listening. Cheers.
Gents, I think we can honestly say that's a fascinating subject and, as always, brilliantly presented. This is an observation with all of the things that are going on with people looking at blocking GPS signals and blocking all the electronics. Do you know what? If there ever was a war to break out, guys, there's probably going to be lots of places for old fart radio amateurs who know their way around this gear. A bit like if you watch that film where they pressed the USS Missouri back in to fight the aliens. Yeah. They're going to need people like us to be able to go out and operate it all.
Here's a question for you. If the balloon ever does go up again, is the RSGB going to coordinate volunteer interceptors? Because there's still people out there.
That's a very good point.
And there's lots, I mean, we've got lots of radios available to us now on the web.
Exactly.
You know.
Mind you, if there's a great big EMP pulse somewhere up in the atmosphere...
Well, they ain't going to be any good, are they?
They're not going to be any good, but those with bottles in them probably will be.
Yeah.
Bear that in mind, guys. Always keep a valve one.